Hello there, and welcome to the Sleepy Science Channel. Tonight, we are drifting into one of the deepest mysteries ever discovered. It is something that surrounds you, passes through you, and outweighs everything you can see in the night sky. It does not shine. It does not glow. And yet, without it, the universe as we know it would never have formed. Dark matter is the unseen architecture of the cosmos. It shapes galaxies, guides their motion, and binds vast structures across unimaginable distances. We cannot touch it or observe it directly, yet its presence is written into the motion of stars and the bending of light itself. Every time a galaxy turns too fast, or a cluster holds together against all expectations, this hidden influence makes itself known. In this journey, we will wander through ideas that stretch from the earliest moments after the universe began to the cutting edge of modern experiments buried deep underground. It is a story filled with unanswered questions, patient observation, and a sense that reality may be far richer than it first appears. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, allow your breathing to slow and let the weight of the day ease away. Allow your body to soften as your mind settles into this vast and fascinating mystery. Let's begin. Dark matter outweighs visible matter, and it shapes every galaxy you see. If you could place the universe on a scale, almost all the weight would come from something that gives off no light at all. The stars, planets, gas clouds, and every glowing nebula would add up to a smaller share than the invisible mass surrounding them. This hidden majority acts like a deep gravitational landscape that ordinary matter settles into. Where that landscape is slightly denser, gas is pulled in, it cools, and it can begin forming stars. Where it is thinner, galaxies struggle to grow. That means the night sky is not only a collection of shining objects, it is also a map of an unseen framework that quietly decides where galaxies appear, how large they become, and how they gather into families across space. Galaxies spin so fast that starlight alone cannot keep them together. Imagine the spinning merry-go-round, where the outer horses race faster and faster as you move outward. That is what astronomers expected for galaxies, if their mass came mostly from what we can see. Instead, many galaxies keep roughly the same rotation speed far from their bright centers. That is a problem, because the outer stars should be flung away over cosmic time. The fact that they remain bound tells us there must be extra gravity holding the system together. One famous case is the Andromeda galaxy, where stars far from the bright disk still move at surprising speeds. Something massive extends well beyond the visible glow, wrapping the galaxy like an invisible anchor. That mismatch between expected motion and observed motion became one of the clearest signposts pointing to unseen matter. Most of the Milky Way's mass is an invisible, extended cloud. If you could fly far above the Milky Way and look back, you would see a bright spiral disk. What you would not see is the much larger region of mass that surrounds it on all sides. This invisible component reaches far beyond the disk, far beyond most of the familiar star fields, and it holds our galaxy together like a deep gravitational basin. Astronomers infer it by tracking the motions of distant halo stars, globular clusters, and small companion galaxies that orbit far from the center. Those objects move as if a great deal of mass is spread through the outskirts where there is little light. This matters for us because our solar system is orbiting within that larger environment. Even the Milky Way's future collision with Andromeda will be shaped by the invisible mass that enfolds both galaxies long before their stars meet. Without dark matter, the early universe would not have built galaxies so quickly. In the young universe, ordinary matter was hot and restless. It was pushed around by radiation, and it did not clump easily at first. dark matter behaves differently. It can begin gathering into denser regions earlier because it does not get held back in the same way. Those early clumps become gravitational seeds. Then, as the universe cools, gas can fall into those seeds and begin forming the first stars and galaxies. This helps explain why we see galaxies already in place when the universe was still relatively young. It also helps explain why those early galaxies could grow into larger systems through merging and accretion. In a sense, dark matter gives the universe a head start on building structure. Without it, the first galaxies would arrive much later, and the cosmos would look far emptier than it does. The biggest cosmic structures look like a web, built by dark matter scaffolding. On the largest scales, the universe is not evenly filled. Galaxies gather into filaments, sheets, and knots, with huge voids in between. This pattern is called the cosmic web, and it is one of the clearest fingerprints of invisible structure formation. Computer simulations that include dark matter naturally grow this web from tiny early ripples, turning them into long strands and dense intersections where galaxy clusters form. Ordinary gas then falls into those gravitational channels and lights up with stars. Over billions of years, the web becomes a kind of cosmic geography, guiding where matter flows and where galaxies thrive. Modern sky surveys map this structure by measuring the positions of millions of galaxies across enormous volumes of space. The astonishing result is that the web is not artistic metaphor. It is a measurable architecture, and it suggests that an unseen framework has been shaping the universe since near the beginning. The idea grew from missing mass problems in galaxy clusters. When astronomers first began treating clusters of galaxies as single objects, they expected the visible members to account for the cluster's gravity. Then the measurements came back, and the numbers refused to cooperate. Galaxies inside clusters were moving far too quickly to remain bound if the cluster contained only what telescopes could see. That meant either the cluster should fly apart, or something heavy was hiding in plain sight. Clusters are perfect places for this mystery to show itself, because they are enormous and long-lived. They act like cosmic laboratories where gravity has had billions of years to reveal its true strength. The missing mass problem was not a small bookkeeping error. It was a loud, persistent mismatch between motion and matter. It hinted that the universe had a deep, unseen component. Fritz Zwicky argued for unseen matter almost a century ago. In the early days of extragalactic astronomy, Fritz Zwicky looked at the Coma cluster and treated it like a swarm of bees in orbit around a shared center. He measured how fast the galaxies were moving and used that motion to estimate how much mass the cluster must contain to stay together. The result was startling. The cluster needed far more mass than the combined light of its galaxies could reasonably represent. Zwicky called the missing component dark matter, and he did it at a time when even the scale of the universe was still being mapped. His claim was bold, and it was easy to doubt, because the evidence was indirect and the idea was uncomfortable. Yet the logic was simple. Gravity leaves footprints in motion. Those footprints said the cluster was heavy beyond what starlight could explain. It was an early warning that the cosmos was hiding something large. Vera Rubin's galaxy rotation work made the mystery impossible to ignore. Decades later, Vera Rubin and her collaborators turned the question into something you could test again and again, galaxy by galaxy. Instead of relying on a single grand system, they measured how fast different parts of spiral galaxies were rotating. They watched the motion of gas and stars at many distances from the center, building a picture of how gravity was distributed. The surprise was not just that something was missing. It was how consistently the same pattern appeared across different galaxies. The outer regions were moving too fast for the visible mass to hold them. The effect was not rare. It looked like a basic rule of galactic life. That changed the tone of the mystery. This was no longer a strange corner case. It was a widespread feature of the universe, repeated across the sky like a refrain that demanded an explanation. Simulations with dark matter recreate the large-scale cosmic web. When cosmologists want to test an idea about the universe, they often build a universe of their own. They start with the faint early ripples seen in the microwave sky. Then they let gravity run forward in time inside a supercomputer. When invisible mass is included, something remarkable happens. The simulated universe grows patterns that match what telescopes map across the real sky. Dense regions form in the right kinds of places. Voids open up where matter drains away. Clusters appear as natural gathering points, rather than as special cases that need extra tuning. The most striking part is that the simulation does not need to know what a galaxy looks like. It only needs the rules of gravity and the right amount of unseen mass. From that, large-scale structure emerges on its own. It is a rare moment in science when a mystery ingredient makes the whole recipe suddenly work. Simulations without it struggle to match observed galaxy clustering. If you run the same cosmic movie without invisible mass, the story becomes strangely quiet. Ordinary matter has pressure, it heats, it cools, and in the early universe it was tightly coupled to intense radiation. That makes it harder for structure to grow quickly and widely. In these dark matter-free simulations, galaxies tend to form too late, and the pattern of their grouping comes out wrong. The universe looks smoother than what surveys actually see. It is like trying to build mountains in a world where the crust never quite grips and buckles. The mismatch shows up in how strongly galaxies cluster, how big the largest concentrations become, and how much structure appears on intermediate scales. This is why dark matter is not only a solution to individual galaxies spinning too fast. It is also a way to get the overall cosmic population of galaxies, groups, and clusters to match the sky we observe. We cannot see it directly, yet we can weigh it by gravity. You do not need light to measure mass. You only need motion. Astronomers watch how stars orbit inside galaxies, how galaxies orbit inside groups, and how hot gas moves inside giant clusters. From those speeds and paths, they can calculate how strong the gravity must be. Then they compare that required gravity to the mass of all the visible material they can count. Again and again, the visible matter comes up short. It is like hearing footsteps in a dark hallway and realizing there must be far more people there than the few you can see. This is why the mystery is so compelling. The evidence does not rest on a single instrument or a single technique. It comes from many kinds of cosmic motions that all point toward the same conclusion. Dark matter forms vast halos, and galaxies live inside them. A galaxy is not only its shining disk or its bright bulge. It is immersed in a much larger region of invisible mass that extends far beyond the last visible stars. This halo acts like a gravitational home that helps a galaxy assemble and remain stable. It also helps explain why smaller galaxies often orbit larger ones in swarms. Those satellites move through the outer halo, like boats riding currents you cannot see. The halo matters for a galaxy's history too. When galaxies pass near each other, their halos can overlap and tug, which can change orbits and trigger long, slow mergers. Over time, halos also gather smaller clumps, which can become future satellite galaxies or be shredded into streams. In this picture, starlight is the decoration. The halo is the main structure that sets the stage. Colliding galaxy clusters reveal separated mass, like a hidden shadow of gravity. Galaxy clusters are the largest bound structures in the universe. When two of them collide, the event becomes a natural experiment on a grand scale. The hot gas in each cluster crashes together and slows down because gas interacts and feels pressure. The galaxies mostly pass through because the distances between stars are enormous. What shocked astronomers is that much of the mass follows the galaxies, not the slowed gas. The best known example is the bullet cluster, where maps of gravity show the main mass offset from the glowing hot gas seen in X-rays. It is as if most of the weight slipped ahead while the visible material got stuck. This separation strongly suggests that the dominant mass does not behave like ordinary matter. It acts like something that barely collides, even during one of the most violent events in the cosmos. Dark matter helps bend light, making distant galaxies look stretched and doubled. Gravity can warp space, and warped space changes the path that light takes. When a massive object lies between us and a distant galaxy, it can act like a natural lens. Sometimes the background galaxy appears stretched into arcs. Sometimes it forms a near-perfect ring. Sometimes it even appears as multiple images of the same object. What makes this so powerful is that the lensing effect depends on total mass, not on brightness. That means astronomers can map invisible mass by studying how it distorts the shapes of background galaxies. In some cases, lensing reveals mass where there are few stars and little glowing gas. It also lets us glimpse galaxies that would otherwise be too faint, because the lens magnifies their light. In this way, the unseen not only shapes what we see, it can also help us see farther than we could on our own. It streams through Earth right now, without leaving an obvious trace. Our planet moves through the Milky Way, and the Milky Way moves through its own dark halo. If dark matter is made of particles, then Earth is constantly passing through that invisible flow. Most of those particles would slip through rock, oceans, and even your body, as if nothing were there. That is why detectors are built in deep underground laboratories, where thick layers of Earth block noisy cosmic rays. Inside, ultra-clean materials wait for a rare moment when a passing particle might nudge an AATOMS nucleus or an electron. The challenge is that almost everything else can mimic a tiny signal, from natural radioactivity to trace contamination. So the experiments are designed like listening rooms for the universe. Even a single convincing event could point to a new kind of matter that has been moving through us all along. Spiral galaxies rotate with surprisingly flat speed profiles far from their centers. If gravity came mostly from the bright stars near a galaxy's middle, you would expect orbital speeds to drop as you move outward. That is how planets behave around the Sun. Instead, many spirals keep moving at nearly the same speed well past the region where most of their light lives. This flatness is like discovering that a carousel keeps the same pace at the edge, even when there is hardly any material there to pull inward. The implication is dramatic. Mass must be spread out in a wide, faint envelope that extends beyond what our eyes can trace. That unseen mass changes how galaxies respond to encounters too. It affects how they tug on neighbors, how their disks stay stable, and how they keep their shape over time. A simple curve of speed versus distance becomes a doorway into the invisible. Galaxy clusters hold hot gas that should escape without extra gravity. In a massive cluster, space between galaxies is filled with superheated gas that shines in X-rays. This gas can be tens of millions of degrees, and at those temperatures, it wants to expand and drift away. Yet clusters keep it trapped for billions of years. The only jailer strong enough is gravity. When astronomers estimate how much gravity is required to confine that hot gas, the visible galaxies do not provide nearly enough. The gas itself is heavy, and in many clusters it outweighs the stars, but even gas plus stars still comes up short. That shortfall is important because the gas is not a guess. X-ray telescopes can measure its temperature and map its distribution, which lets scientists calculate the pressure trying to push it outward. The fact that the gas remains bound tells you the cluster is wrapped in extra mass you cannot see. Gravitational lensing maps mass where no starlight exists. Sometimes the universe draws you a map without using ink. When a foreground galaxy or cluster sits in front of a more distant scene, gravity bends the paths of arriving light. Background galaxies appear distorted, shifted, and stretched into arcs. By measuring those distortions, astronomers can reconstruct where the lensing mass must be, even if that mass is not glowing. This is powerful because it does not rely on how matter behaves internally. It relies on geometry and the curvature of space. In some observations, the strongest lensing signal comes from regions with little visible material. That tells us the weight is real, even when the light is missing. Lensing also allows nature to magnify extremely distant galaxies, turning telescopes into time machines. In a single image, you can see the hidden mass in the foreground and the amplified ancient universe behind it. Weak lensing reveals subtle alignments across millions of distant galaxies. Not all lensing is dramatic. Most of it is whisper quiet. A single distant galaxy might be stretched by only a tiny amount, too small to trust on its own. But when you measure the shapes of millions of galaxies, patterns emerge. The tiny distortions line up across wide regions of sky, and those alignments trace the distribution of mass between us and them. This is called weak lensing, and it is one of the most elegant ways to see the invisible. It works like reading wind direction from a field of grass. One blade does not tell you much. A whole meadow does. With careful statistics and careful control of telescope effects, weak lensing maps can reveal filaments, dense nodes, and empty regions, even when those structures contain little starlight. It turns the entire sky into a detector, using distant galaxies as the measuring grid. Strong lensing can produce Einstein rings from a single background galaxy. Under the right alignment, gravity becomes a cosmic sculptor. If a massive foreground object sits almost perfectly in front of a distant galaxy, the light can wrap around the lens and form a circle. That circle is an Einstein ring. It is not an artistic trick. It is the background galaxy being imaged along many different paths through curved space. The size and thickness of the ring depend on the mass and its distribution in the lensing object. This lets astronomers measure that mass with striking precision, including the parts that do not shine. Strong lensing can also split a single galaxy into multiple images, which arrive along different routes and can even show time delays if the background source gray. Varies. Each image is a clue, and together they act like a puzzle that reveals the lens's hidden structure. It is gravity turning space into a lens you can actually measure. The cosmic microwave background records dark matter's early gravitational imprint. Long before stars existed, the universe was filled with hot plasma and light that scattered constantly. When the universe cooled enough for atoms to form, that light finally traveled freely. We still see it today as the cosmic microwave background, a faint glow coming from every direction. It looks smooth at first glance, but it carries tiny variations in temperature. Those small variations are not random decoration. They reflect early differences in density and pressure that later grew into galaxies and clusters. Dark matter plays a key role here because it adds gravity without getting tangled in the same light-driven push and pull that affected ordinary matter. Its presence changes how those early patterns rise and fall, leaving a distinct signature in the microwave sky. By measuring that signature with exquisite precision, scientists can estimate how much invisible matter exists, even though the microwave background itself, made of light. Tiny temperature ripples hint at invisible matter shaping the first structures. Those faint ripples in the microwave background are incredibly small, yet they carry a cosmic story. They show where matter was slightly denser, where gravity pulled a little harder, and where the early universe began to organize itself. Over time, dense regions grew denser, and emptier regions became vast voids. Dark matter helps explain how this growth could begin early and proceed efficiently. The ripples act like a blueprint at the moment the universe became transparent. From that blueprint, scientists can run forward the clock with simulations and compare the result to the distribution of galaxies we see today. When the match works, it is a powerful sign that the invisible component is real and that it behaved in a particular way. It is astonishing that a faint afterglow from the young universe can tell us about a form of matter we still cannot capture directly. The earliest light becomes evidence for unseen weight. Dark matter clumps early, while ordinary matter stays pressure-smoothed longer. In the universe's first chapters, ordinary matter was not free to gather wherever gravity wanted. It was mixed with radiation in a hot, dense plasma, and that radiation pushed back whenever matter tried to clump. Think of it like trying to form fog into droplets while a strong wind keeps stirring the air. Invisible matter is different because it does not couple to light in the same way. It can begin collapsing into denser patches earlier, building a network of gravitational wells long before atoms formed. Later, when the universe cools and ordinary matter becomes neutral, gas can finally respond more easily to those wells. This sequence matters. It means the invisible component sets the early rhythm of structure formation, and ordinary matter joins in once the cosmic environment allows it. The timing is a key reason galaxies could appear when the universe was still young. This early clumping seeds the first star-forming regions. The first stars did not ignite in empty space. They needed places where gas could gather, cool and compress until gravity took over completely. Early halos of unseen mass provided those gathering points. Gas fell in, heated up, and then began to shed that heat through simple molecules. One of the most important was molecular hydrogen, which can radiate energy away even when heavy elements are scarce. As the gas cooled, it sank deeper, became denser, and eventually fragmented into the first star-forming clouds. Those first stars were likely very different from most stars today, because the early universe had almost no carbon, oxygen, or dust to help cooling. This makes the first star-forming regions feel like a delicate cosmic balancing act, with invisible gravity providing the stage and primitive chemistry providing the final push. In that sense, dark matter helped set the conditions for the first starlight to appear. Dark matter does not seem to make or absorb light. One of the strangest clues is also the simplest. If this missing mass interacted with light the way normal matter does, we would see it. It would glow when heated. It would cast shadows by absorbing or scattering radiation. It might show up as extra dust, extra gas, or extra faint stars. Instead, it behaves as if it is almost perfectly transparent to electromagnetic light. That forces astronomers into a different kind of observing. They look for its pull, not its shine. They map its influence through motion and through lensing, rather than through images that resemble ordinary objects. This transparency also narrows the list of possibilities in particle physics, because any candidate must be able to hide from the entire electromagnetic spectrum. The result is both frustrating and thrilling. The universe is telling us that something massive is present, and it is also telling us that our usual ways of seeing are not enough. It also does not appear to interact strongly with ordinary atoms. If invisible matter collided often with normal atoms, the universe would feel crowded in an obvious way. Gas clouds would heat differently. Stars might lose energy faster. Planets and people might experience a faint drag as they move through space. None of that is seen. Instead, the evidence suggests that ordinary matter and dark matter mostly pass through each other. That is why experiments search for incredibly rare interactions, the kind that might happen only after long waiting in an ultra-quiet detector. This weak coupling is also why dark matter can remain spread through galactic halos without clumping into glowing disks the way gas does. It does not radiate away energy efficiently, and it does not bump into itself or into atoms in the same frequent way. The picture that emerges is of a vast population of particles that behave like ghosts with weight. They shape structures through gravity, while refusing to join the ordinary chemical story of the universe. Dark matter seems cold, meaning it moves slowly compared with light. The word cold here does not mean temperature in the usual sense. It means the particles move relatively slowly, so they do not wash out small structures as the universe evolves. If dark matter were racing around near the speed of light, it would behave like a smoothing brush, erasing small clumps and delaying the formation of compact halos. Instead, the observed richness of structure suggests that the invisible component had low random speeds early on. This helps small halos survive and merge into larger ones, building a universe with plenty of variety in scale. Cold dark matter also produces specific predictions in simulations, such as many small substructures orbiting within bigger halos. Whether those predictions match reality in every detail is still being tested, and that is part of the excitement. The key point is that the universe's fine-grained structure acts like a speedometer. It hints that whatever dark matter is, it likely did not spend cosmic history zipping around too quickly to gather. Warm, dark matter would smooth away small galaxies and early clumps. Now imagine the invisible particles moving faster in the early universe. They would drift out of small density peaks before gravity could pull them in, and that would wipe out the tiniest structures. The result would be fewer small halos, fewer early building blocks, and a different pattern of galaxies on the smallest scales. This idea is tempting because it might address certain small-scale tensions, yet it must still match what we observe in intergalactic gas and in the abundance of faint galaxies. Astronomers test these models by looking at delicate cosmic tracers that preserve small-scale information, almost like fossil ripples. If warm dark matter is too warm, the universe becomes too smooth in places where it is clearly not smooth. So the speed of dark matter becomes a measurable property, even without catching a particle. It is constrained by the mere fact that small structures exist, and that they appeared early enough to fit the story of cosmic history. Fuzzy dark matter would behave like waves on galactic scales. Some proposals take a very different turn. Instead of thinking of dark matter as tiny particles acting like grains, imagine it as an ultra-light quantum field with a wavelength that can span a galaxy. In that case, its behavior would resemble waves, with interference patterns and a kind of quantum pressure that resists being squeezed too tightly. This could naturally soften the very center of a halo, because the wave nature prevents an infinitely sharp pile-up. It also means that instead of countless tiny clumps, structure on the smallest scales might blur into a smoother distribution. The idea sounds almost poetic, yet it makes concrete predictions. The centers of galaxies could develop characteristic core shapes, and the distribution of small-scale structure could differ from standard expectations. Testing it requires precise observations of galaxies where gravity dominates, and where the details of inner mass matter most. It is an example of how the dark matter mystery might connect the largest objects in the universe to the strangest rules of quantum physics. Self-interacting dark matter could soften dense galaxy centers. Another possibility is that dark matter does interact, just not very much with ordinary matter. It might scatter off itself. Even a modest amount of self-scattering could change how halos evolve over billions of years. The densest inner regions could become less sharply peaked, because interactions would move energy around and gently puff up the core. That could help explain why some galaxies appear to have smoother central mass distributions than simple cold models predict. Yet the idea has to survive harsh tests on larger scales. In massive clusters, dark matter seems to pass through mergers with limited drag, and that places bounds on how strong any self-interaction can be. So the concept sits in a narrow, fascinating corridor. Too little interaction changes nothing. Too much interaction breaks what we see in clusters. Somewhere in between, it could resolve long-standing puzzles and reveal an unseen form of matter with its own subtle internal physics, shaping galaxies from the inside out. Some galaxies appear to have unusually little dark matter for their size. A few faint galaxies have surprised astronomers by behaving as if they contain far less invisible mass than expected. They are still held together, and they still have stars moving inside them. Yet the usual gravitational excess seems muted. One widely discussed example came from the Dragonfly telephoto array, which helped spotlight a galaxy called NGC 1052 DF2. Early measurements suggested its stars move more slowly than they should if a heavy halo were present. That sparked a lively debate, because small changes in distance estimates can change the mass story dramatically. Another possibility is that environment matters. A close encounter with a larger galaxy could strip away invisible material more easily than stars. If these galaxies truly lack dark matter, they challenge the idea that every galaxy forms inside a massive halo. They become rare, puzzling exceptions that sharpen our questions. Other galaxies are so diffuse that dark matter dominates almost everything. Some galaxies look like ghosts, with so few stars spread so widely that they barely stand out from the background sky. These are called ultra-diffuse galaxies, and they can be enormous in size, while remaining remarkably dim. In some cases, their stars move as if a heavy, unseen halo is doing most of the gravitational work. One famous candidate is Dragonfly 44, where early studies suggested an unusually large amount of invisible mass for the amount of starlight present. That creates a startling picture. A galaxy can be big and faint, yet still sit inside a deep gravitational well. How does something like that form? Perhaps it began like a normal galaxy, then lost gas before it could build many stars. Perhaps it was puffed up by encounters inside a cluster. Each possibility turns these delicate-looking systems into powerful tests of how invisible structure shapes visible outcomes. Dwarf galaxies are dark matter laboratories because they have few bright stars. Dwarf galaxies are small, faint, and often chaotic, yet they may be some of the most important objects in the sky. Because they contain relatively little ordinary matter, they offer a cleaner view of the invisible mass that dominates their gravity. Astronomers measure this by tracking how stars move inside them. If the stars zip around faster than the starlight can explain, the extra pull points to a heavy halo. Ultra-faint dwarfs are especially intriguing because they can contain only a tiny sprinkling of stars while still being strongly bound. That creates extreme mass to light ratios that feel almost unreal. These galaxies also preserve ancient stars, which carry chemical clues from the early universe. So in one small system, you can study both the hidden gravitational framework and a fossil record of early cosmic history. That combination makes dwarfs irresistible. Satellite galaxies around the Milky Way test dark matter on small scales. The Milky Way is surrounded by a menagerie of smaller companions, from bright satellites like the Large Magellanic Cloud to ultra-faint dwarfs discovered in modern surveys. These satellites orbit through our galaxy's halo, and their fates are shaped by invisible tides. Some are stretched into elongated shapes. Some are being torn apart into streams. Their internal star motions also reveal how strongly they are bound, which hints at how much unseen mass they contain. This matters because small scales are where many dark matter models begin to differ. If halos are packed with tiny clumps, satellites should be affected in one way. If the invisible components smooth structure, satellites should look different. New data on satellite proper motions lets astronomers reconstruct past orbits, which helps reveal how much stripping occurred and when. Each companion becomes a probe you can track across the sky, like a test particle moving through an invisible field. The missing satellites puzzle asks why we see fewer dwarfs than expected. When scientists run cold dark matter simulations of a Milky Way-sized halo, they often produce a swarm of many small subhalos. For years, telescopes did not seem to find nearly that many dwarf galaxies. This mismatch became known as the missing satellites puzzle, and it raised an awkward question. Are the simulations wrong, or are most small halos simply dark? One promising answer is that many subhalos never formed many stars. Reionization and stellar winds can heat or remove gas from tiny halos, leaving them nearly invisible. Another answer is that our census was incomplete. Ultra-faint dwarfs are hard to spot, and modern surveys have been steadily adding new members to the list. The puzzle is now a moving target, which is exactly what makes it exciting. Every new dwarf discovery updates the test, and every non-discovery keeps the mystery alive. The too big to fail problem challenges how dense some predicted dwarfs should be. Even when simulations produce many subhalos, a deeper tension can appear. Some of the most massive predicted subhalos should be dense enough that they almost have to form stars. Yet the Milky Way's known bright dwarfs do not always seem to live in halos that dense. That gap is called the too big to fail problem. It is not about the tiniest halos that could plausibly remain dark. It is about halos that seem too substantial to have failed at forming a visible galaxy. Several solutions are on the table. Strong bursts of star formation could have rearranged inner mass over time. Tidal interactions with the Milky Way could have reduced densities. It is also possible that our galaxy is unusual compared with the average case. However it resolves, the problem has teeth because it connects precise measurements of stellar motions in nearby dwarfs to the fundamental nature of invisible matter. The core cusp debate asks if dark matter centers are steep or flat. In many simple cold dark matter simulations, halos develop dense inner regions where the mass rises sharply toward the center. That steep rise is called a cusp. Yet observations of some dwarf and low surface brightness galaxies suggest their inner mass may be distributed more gently, forming a flatter core. This debate matters because the inner shape of a halo is a fingerprint of how dark matter behaves and how galaxies evolve. If the difference is real, it could hint at new physics, such as self-interactions, or it could reveal the long-term influence of ordinary matter. A galaxy is not only a passive tracer of a halo. Gas can flow, stars can explode, and gravity can respond. Over time, repeated changes in the central potential could soften a cusp into a core. The challenge is that measuring inner mass is hard. It requires careful modeling of star motions, gas rotation, and viewing geometry. That is why this debate remains active and why every improved observation feels like progress. Stellar feedback might reshape dark matter by stirring the inner gravity field. Stars are not quiet residents of a galaxy. Massive stars flood their surroundings with radiation, and their deaths as supernova can shove gas around with enormous force. If gas is repeatedly pushed out from the center and then falls back in, the gravitational field near the center changes again and again. Dark matter responds to those changes. Over many cycles, the invisible particles can be nudged onto wider orbits, which lowers the central density. This mechanism offers a way to reconcile steep simulated cusps with flatter observed cores, without changing the fundamental nature of dark matter. It also makes a specific prediction. Galaxies with the right history of bursty star formation should show the strongest reshaping, while very tiny dwarfs that never formed many stars might keep it. Original inner structure. That creates a rich connection between how stars live and die and how invisible matter arranges itself, linking astrophysics and cosmology in a single bar. Story. Tidal stripping can peel dark matter away from small orbiting galaxies. As a dwarf galaxy orbits a larger host, it experiences changing gravitational forces across its body. The side closer to the host is pulled harder than the far side. Over time, that difference can tear material away. Dark matter is often the first to go because it extends farther out than the stars and is less tightly bound at the edge. The dwarf can lose much of its halo while its stars remain, at least for a while, still clumped enough to be seen. This process can explain why some satellites look disturbed or elongated. It can also produce faint streams of stripped material that wrap around the host in long arcs. Tidal stripping is not only destruction, it is also a tool. By modeling how much mass must be removed to match what we observe, astronomers can infer the original halo and test how resilient dark matter structures are. Each satellite orbit becomes a slow experiment conducted by gravity itself. Streams of stars can act like ink, tracing dark matter's hidden lumps. When a globular cluster or dwarf galaxy is gradually torn apart, its stars do not vanish. They spread into long, narrow streams that continue to orbit the galaxy. These stellar streams are exquisitely sensitive to disturbances. If the gravitational field were perfectly smooth, a stream would remain thin and coherent for a long time. If invisible subhalos lurk in the halo, their flybys can punch gaps, create spurs, or thicken the stream. That means a stream can function like a seismograph for unseen structure. It records past encounters in its shape. This approach is exciting because it does not require dark matter to interact with detectors on Earth. It uses gravity alone, written into the sky. Observatories that map precise stellar positions and motions can turn these streams into detailed diagnostics. The reward is a way to test whether halos are filled with small clumps, which is one of the defining predictions of cold dark matter. The galaxy becomes a canvas, and the streams become the ink. Gaia is mapping stellar motions that help reveal the Milky Way's dark halo. Instead of taking a photograph of the galaxy, Gaia is taking a choreography. It measures how stars drift across the sky and how they move along our line of sight. Then it turns those motions into a three-dimensional map of orbits. Those orbits respond to gravity, even when most of the mass is invisible. When researchers model the paths of halo stars, star clusters, and distant companions, they can infer the shape and extent of the unseen mass that surrounds the Milky Way. Small mismatches matter. A slightly different halo shape can change where an orbit precesses and how quickly a population spreads out. Over time, Gaia's precision helps separate what belongs to the disk, what belongs to the bulge, and what belongs to the larger halo. It is a way of weighing the invisible using the calm, persistent drift of starlight. The fastest stars can hint at how heavy our galaxy truly is. Some stars move so quickly that they seem almost impatient to leave. A few are flung outward after close encounters with dense star groups or with the supermassive black hole at the galaxy's center. Once launched, they race through the Milky Way's outskirts like test probes. Their speed, and whether they remain bound or escape, depends on how deep the galaxy's gravitational well is. If the halo is massive and extended, even very fast stars can be slowed and turned back. If the halo is lighter, those same stars can sail into intergalactic space. Astronomers track these speedsters over years, measuring both their motion across the sky and their radial velocity. Each trajectory becomes a story about gravity on scales far beyond the bright disk. It is a thrilling idea. A single runaway star can carry news about the unseen mass that holds our whole galaxy together. The escape speed of the Milky Way depends on unseen mass. Every gravitational system has a speed limit that separates returning from leaving for good. For Earth, that number is familiar from rocketry. For a galaxy, it is far larger and far harder to measure. Astronomers estimate the Milky Way's escape speed by studying the fastest stars in the solar neighborhood and by modeling how likely different velocities are. If the escape speed is high, the galaxy must contain more mass spread over a larger region. If it is lower, the halo must be less massive or less extended. This measurement is powerful because it does not require you to see the halo. It only requires you to understand what speeds are even possible in the local gravitational landscape. It also connects to the galaxy's history. A heavier halo can capture more incoming material over cosmic time. A lighter halo may have lost more along the way. Dark matter may influence how long-lived star streams stay thin. When a stellar stream is freshly formed, it can be remarkably narrow, like a ribbon laid across the sky. Over time, that ribbon can thicken and blur, and the rate of that change depends on the gravitational environment it travels through. A smoother halo allows a stream to remain coherent longer. A more structured halo stirs it, heats it, and gradually makes it puffier. This turns stream thickness into a kind of clock. If a stream stays thin for a long stretch, it hints that the surrounding gravitational field has been relatively calm. If it fans out quickly, it suggests a more complex halo with more internal structure. Astronomers use precise stellar positions and velocities to reconstruct how a stream has evolved. Then they compare those reconstructions to different halo models. In that way, the quiet survival of a delicate stream can tell you about the invisible landscape it has been crossing for billions of years. Gaps in streams can signal tiny dark clumps passing through. A long stellar stream can look smooth from a distance, yet close inspection can reveal missing sections, strange kinks, or small offshoots. One way to make such features is for an unseen clump of mass to pass nearby. The stream's stars feel a brief gravitational tug, and their orderly spacing is disturbed. Over time, that disturbance can widen into a visible gap or a spur. The fascinating part is scale. The clump does not need to be as large as a galaxy. It can be a dark subhalo with little or no starlight at all. Researchers search for these signatures by mapping streams in detail and by modeling what different kinds of flybys would produce. When the match is convincing, it offers evidence for a population of small, mostly invisible structures orbiting within the Milky Way's halo. It is like detecting an unseen fish by the wake it leaves in a long ribbon of floating leaves. The Large Magellanic Cloud drags on our halo through gravity. The Large Magellanic Cloud is not just a bright companion in the southern sky. It is a hefty visitor that is currently moving through the Milky Way's outer regions. As it travels, its gravity pulls on the surrounding dark halo, and the halo responds by forming a trailing overdensity called a wake. That wake then tugs back on the cloud, a process known as dynamical friction. The result is a slow exchange of momentum that can change orbits over time. Astronomers look for this effect in the motions of distant halo stars and in the shifting paths of satellites whose orbits may have been nudged. This is exciting because it turns the halo into something almost tangible. You can imagine it as a sea that can be disturbed, even though it is invisible. By measuring the size and shape of the wake, researchers can learn about the halo's density and how it is distributed far from the galactic disk. Galaxy bars rotate, and their slowing can test dark matter density. Many spiral galaxies have a central bar, a long structure of stars that rotates like a rigid pattern through the disk. That rotating bar is not alone. It moves through the surrounding halo, and gravity creates a kind of drag as the bar exchanges angular momentum with the unseen mass. If the inner halo is dense, the bar should slow more noticeably over cosmic time. If the inner halo is less dense, the bar can stay fast, with its rotation tied closely to the visible disk. Astronomers estimate bar pattern speeds by measuring how stars and gas respond to the bar's rotation. Then they compare those pattern speeds to what different halo densities would allow. This is a clever test because it uses an internal galactic feature as a probe of invisible matter. The bar becomes a natural rotor placed inside an unseen medium, and its long-term behavior reveals how much hidden mass is in the way. Dark matter may help set where galactic disks become stable. A disk of stars and gas is a balancing act between gravity, pressure, and rotation. Too little support, and parts of the disk can collapse into clumps. Too much, and the disk can remain smooth, forming stars more slowly. The surrounding halo influences this balance by adding gravity and by shaping the overall rotation curve that keeps the disk in orbit. A deeper halo can stabilize some regions against large-scale distortions, while still allowing smaller patches to collapse and form stars. It can also affect where spiral arms become prominent and how easily a disk develops a bar. This means the halo is not just a container. It is an active participant in a galaxy's visible architecture. When astronomers compare galaxies with similar disks but different rotation behavior, they can infer differences in halo support. In a quiet way, invisible mass helps decide whether a disk becomes clumpy, calm, strongly barred, or richly spiral. Dark matter halos may be triaxial, not perfectly round. It is tempting to picture a halo as a smooth sphere, but gravity does not always build symmetry. In many models, halos form with three unequal axes, more like a stretched potato than a ball. That shape matters because it changes how orbits precess and how debris spreads when smaller systems are torn apart. Observations can test this by examining the paths of tidal debris in the Milky Way, including the long Sagittarius stellar stream that wraps around the sky. If the halo were perfectly round, the stream would follow a simpler track. If the halo is triaxial, the stream's path and thickness can shift in characteristic ways. Astronomers also study the distribution of satellite galaxies and the motions of distant halo stars to look for consistent signs of asymmetry. A non-spherical halo would tell us something about how the Milky Way assembled and how the invisible component responds to the pull of the disk. Shape becomes another clue to the nature of the unseen. Some halos may rotate slowly, adding subtle twists to galaxy dynamics. Rotation is not only for stars in disks. The unseen halo may carry angular momentum too, gained through ancient mergers and long gravitational torques. If a halo rotates even modestly, it can slightly change the balance of forces felt by orbiting stars and satellites. Over time, that can shift orbital planes, alter how bars exchange momentum, and influence the direction that debris spreads after a merger. Halo rotation also matters for Earth-based searches. The relative motion between our solar system and the local dark matter distribution affects the speeds of incoming particles in a detector. A rotating halo could tilt that speed distribution and change when the fastest particles are most likely to arrive. Detecting such a slow spin is challenging because the halo is not a solid object. It is a vast population. Still, hints can emerge from the coherent motion of halo stars and from the dynamics of satellites. If confirmed, it would be a reminder that the invisible is not static. It has history, motion, and memory. Ordinary matter can be dark too, but it cannot explain the full deficit. Astronomers first asked a sensible question. What if the missing mass is ordinary stuff that simply does not shine? Cold gas, faint dust, dim stars and burned-out remnants can all hide from casual observation. The trouble is that ordinary matter leaves fingerprints. Gas absorbs and emits at specific wavelengths, and dust reshapes light in telltale ways. Even when it stays dark, it still interacts with radiation and with itself. On cosmic scales, there is another limit. The early universe set the amount of normal matter through the way light elements formed and through precise patterns in the microwave sky. Those independent measurements agree with each other, and they leave too little ordinary material to account for the extra gravity in galaxies and clusters. So some darkness is familiar, but the dominant darkness appears to be something else entirely. Hidden planets and faint stars were tested, and they fall far short. For a long time, one tempting idea was that the halos of galaxies might be filled with faint objects. Think of wandering planets, brown dwarfs, dead stars, and other compact bodies that barely glow. Collectively, these are sometimes called massive compact halo objects. If enough of them existed, they could add weight without much light. The universe, however, provides a clever way to test this. When a compact object passes in front of a distant star, its gravity briefly magnifies the star's light. The star brightens in a smooth, distinctive way, then returns to normal. By monitoring huge numbers of stars over many years, astronomers can count how often these events occur. The result is sobering. There are not enough of these hidden bodies to make up most of the missing mass. They may contribute a little, yet the main mystery remains. Microlensing surveys strongly limited compact dark objects in many mass ranges. Microlensing searches became a patient kind of stargazing. Telescopes watched dense fields of stars in the Magellanic Clouds and toward the galactic bulge, looking for brief brightenings caused by gravity alone. Each event carries information about the lens, including a rough sense of its mass and speed. Over time, the statistics built up. If the Milky Way halo were packed with compact objects of a particular mass range, the sky would sparkle with lensing events at a predictable rate. Instead, the observed rate was too low to support that picture across wide ranges of possible masses. This does not eliminate every possibility, but it closes many doors that once seemed open. It also shows how creative the search has become. Dark matter is not being hunted with one tool. It is being cornered by many independent methods, each looking for a different kind of footprint. Neutrinos exist and are dark, but they are too light to build galaxies. Neutrinos are real, abundant, and famously elusive. Trillions pass through you each second, and most never interact with anything at all. That sounds like a perfect recipe for dark matter, until you consider how they move. Because neutrinos are so light, they travel extremely fast, especially in the early universe. Fast-moving particles do not settle into small gravitational wells easily. They smear out, streaming from dense regions into emptier ones. A universe dominated by neutrinos would struggle to form small structures early, and it would build galaxies in a different pattern than what we observe. Cosmological measurements also place strict limits on the total neutrino mass, which keeps their overall gravitational contribution modest. So neutrinos are part of the cosmic inventory, and they do contribute some unseen mass. They are simply not heavy or slow enough to be the main architect of galaxies. A leading idea is a new particle that barely touches normal matter. The most exciting possibility is also the most unsettling. The missing mass might be a new kind of particle that our current theories do not include. It would have mass, it would respond to gravity, and it would rarely interact with atoms, light, or familiar forces. That would explain why it collects into halos without forming glowing disks, and why it has remained hidden despite a century of astronomy. Particle physicists imagine candidates that are stable over cosmic time, which is essential if they still fill the universe today. They also require the right abundance. Too many would overfill the cosmos, and too few would fail to explain galactic motions. This idea turns the sky into a laboratory for fundamental physics. The distribution of galaxies becomes evidence about a particle we have never produced on Earth. It is a rare bridge between the very large and the very small. WIMP were once favorites, but experiments have tightened the net dramatically. For years, weakly interacting massive particles felt like the leading suspects. The appeal was almost poetic. A particle with roughly the right mass and interaction strength could naturally be produced in the early universe in just the right amount. That miracle made WIMP a central target for detectors deep underground and for searches in space. Yet as the years passed, the expected signals did not appear. The experiments became larger, cleaner, and more sensitive. The absence of detections began to rule out broad regions of the simplest WIMP parameter space. This does not mean the idea is dead, but it has changed the mood. The hunt has grown more adventurous. Researchers now consider WIMP with weaker interactions, different masses, or more complex behavior. The story is still thrilling because a non-detection is not nothing. It is a narrowing of the possible, which is how science advances in the dark. Actions are another candidate, born from a solution to a strong force puzzle. Actions entered the story from an unexpected doorway. They were proposed to solve a subtle problem in the physics of the strong nuclear force. A problem about why certain symmetries appear unbroken when they could have been. In the process, the solution predicted a new particle that would be light, stable, and extremely hard to detect. Those properties make actions appealing as dark matter. Unlike heavy particles that might strike a nucleus, actions are often searched for as a background field that can convert into microwaves in a strong magnetic environment. Experiment build resonant cavities, tune them like radios, and listen for a faint, narrow signal that would betray a cosmic sea of actions. What makes this captivating is the double reward. Finding actions could explain a deep particle physics puzzle and the missing mass of the universe at the same time. It is rare to aim one experiment at two mysteries. Sterile neutrinos could exist, interacting only through gravity and mixing. Sterile neutrinos are a quieter cousin to the neutrinos we know. They would not feel the weak nuclear force in the usual way, which means they would be even harder to detect. They might still influence ordinary neutrinos through subtle mixing, like two musical notes that can trade resonance. If they exist with the right mass and lifetime, they could contribute to the universe's dark matter, especially in a warm regime that changes small-scale structure. Astronomers look for indirect hints, including faint X-ray features that could arise if such particles decay very slowly over cosmic time. The evidence is not settled, and that uncertainty is part of the intrigue. This candidate sits at an intersection. It touches particle physics, cosmology, and astrophysical observation. It also reminds us that dark does not have to mean completely isolated. A particle can be almost hidden, yet still leave delicate traces that careful instruments might one day reveal. Primordial black holes are possible, formed before stars ever existed. Black holes usually bring to mind the deaths of massive stars, but the early universe could, in principle, have made black holes directly. In the first moments after the Big Bang, regions with slightly higher density might have collapsed under their own gravity, forming black holes without any stars involved. If enough formed in the right mass range, they could contribute to the missing mass. This idea is dramatic because it replaces new particles with an extreme form of known physics. It is also constrained from many directions. Too many black holes of certain masses would disrupt stellar systems, alter cosmic backgrounds, or produce lensing signals we would have already noticed. Still, there remain windows where primordial black holes could hide. The concept keeps attention because it connects dark matter to the universe's earliest fluctuations. It turns the question into one about how lumpy the infant cosmos was, and what those lumps could become. Any single candidate must fit cosmology, galaxies, and laboratory constraints together. Dark matter is not one mystery. It is a whole network of clues that must agree with each other. A candidate must reproduce the pattern of structure seen across the sky, including the growth of galaxies and the clustering measured by surveys. It must also match the cosmic microwave background, which acts like a snapshot of early conditions with extraordinary precision. On top of that, it must survive limits from direct detection, indirect searches, and collider experiments, all of which probe different kinds of interactions. This is why the problem is so hard, and also why it is so exciting. A viable answer cannot be merely plausible in one corner. It must thread a needle through the entire universe. That makes the eventual solution feel like it will be profound. When something fits every scale, it stops being a guess and becomes part of our understanding of reality. Direct detection looks for tiny nuclear recoils from passing dark particles. The dream is simple. Catch the slightest tap from an invisible visitor. In a direct detection experiment, a dark matter particle would pass through a detector and collide with an atomic nucleus, giving it a tiny kick. That kick is so small that you would miss it in everyday noise, so the entire experiment is built like a silence chamber. Researchers look for a very specific pattern, a short burst of energy that matches what a nucleus recoil should look like. They also compare how often recoils appear at different energies, since different particle masses would produce different recoil signatures. The challenge is that normal background events can imitate the signal, which is why experiments rely on multiple detection channels and strict controls. If a consistent recoil pattern emerged across different materials and sites, it would be a landmark discovery. It would be the first non-gravitational touch from the universe's hidden mass. Underground labs hide from cosmic rays to hear faint signals. On the surface, space is always knocking. Cosmic rays strike the atmosphere and create showers of particles that can penetrate buildings and mimic rare events. That noise is disastrous when you are hunting for something that might interact only a handful of times per year, or not at all. So detectors are carried deep underground, into mines and mountains, where layers of rock act like a natural shield. Even there, scientists add more protection. They surround experiments with water tanks, lead, copper, and active veto systems that can tag intruders. They select materials with extremely low natural radioactivity, and they clean components as if they were preparing a surgical room. In this environment, every background event becomes a suspect with a known origin. The goal is not only to reduce noise. It is to understand what remains so well that anything unexpected stands out clearly. Going underground is a way of giving the universe a quieter microphone. Liquid xenon detectors watch for flashes and charges from rare impacts. Liquid xenon has become a star material in the search because it can respond in two useful ways at once. If something deposits energy inside the liquid, it produces a brief flash of light. It can also free electrons, which are then drifted upward by an electric field into a gas layer, where they make a second signal. The timing between the two signals tells you the depth of the event, and the pattern on sensors helps locate it sideways. This three-dimensional positioning matters because backgrounds tend to cluster near detector walls, while the cleanest region is deep in the center. Xenon also scales well. You can build very large targets while keeping the material chemically stable and comparatively self-shielding. The result is an instrument that can reject many types of false events and focus on a narrow signature window. When xenon detectors get quieter, they do not just listen longer. They listen more intelligently. Some experiments search for annual modulation as Earth changes its motion. Earth is not standing still. It orbits the Sun, and the Sun moves through the Milky Way. If dark matter forms a halo around our galaxy, that motion could create a changing headwind of dark particles. In one part of the year, Earth's orbital velocity adds to the Sun's motion, so the detector would move slightly faster through the halo. About half a year later, Earth's motion partly subtracts, making the relative flow slightly slower. This could produce a small annual rise and fall in event rate, a kind of seasonal rhythm in the data. The appeal is that many backgrounds do not naturally follow the same phase and stability over many years. The risk is that some environmental effects can also vary seasonally, and they must be ruled out with care. Modulation searches therefore demand long data sets, consistent operating conditions, and careful cross-checks. If a modulation appears with the right timing in multiple detectors, it would be a strong and beautifully simple clue. The Dharma result remains debated because other detectors do not confirm it. In an underground laboratory in Italy, the Dharma and Dharma Libre experiments have reported an annual modulation signal for many years. The claim is not that they have seen a single, unmistakable dark matter event. The claim is that the overall rate in a certain energy range rises and falls with a steady yearly pattern. That is provocative, because it resembles what a changing halo wind might produce. The debate is intense because other experiments using different detector materials and different background controls have not seen compatible signals in the same BAL. Dark matter interpretations. That leaves several possibilities. The modulation that arise from an unrecognized background that also varies annually. The signal could be real, yet depend on an interaction type that other experiments are less sensitive to. Or the assumptions that connect different detectors could be incomplete. What makes this important is not only the controversy. It is the discipline it forces. It pushes the field to compare methods, share calibration ideas, and test subtle seasonal systematics with extreme rigor. Cryogenic crystals can feel minute vibrations from a single collision. Some detectors do not chase light first. They chase heat, at temperatures so low that a tiny deposit of energy becomes noticeable. In cryogenic crystal experiments, a collision inside a crystal creates a burst of vibrations called phonons. Those phonons are, in effect, sound at the atomic scale. Sensitive sensors attached to the crystal can detect the resulting change in temperature and the flow of phonons, even when the total energy is minuscule. Many designs also measure ionization at the same time, which helps separate nuclear recoils from electron recoils. The combination gives powerful background rejection, especially in the low energy region where some models predict signals. The technology is demanding because it requires stable, ultra-cold operation and careful control of microphonic noise and radioactivity. Yet it offers something special. It turns a solid crystal into a musical instrument for rare physics. If a dark particle strikes, the crystal does not just register it. It rings, and the sensors listen for the distinctive note. Some searchers target electron recoils for lighter dark matter candidates. If dark matter particles are very light, they might not be able to shove a heavy nucleus enough to make a detectable recoil. They might instead interact with electrons, which are far easier to jostle. That changes the strategy. Experiments look for small ionization signals, tiny bursts of scintillation light, or specific excitations in semiconductors and noble liquids. The difficulty is that electron recoils are common in ordinary backgrounds, including beta decays and gamma interactions. So these searches rely on careful spectral shapes, event topology, and extremely low contamination. They also explore new materials, such as silicon and germanium devices, designed to measure single or few electron events. The excitement is that this opens a wider landscape of possibilities. Dark matter might not be heavy and rare in its interactions. It might be light, abundant, and subtly present in electronic degrees of freedom. By listening for electron-scale whispers, these experiments probe a region of physics that older nuclear recoil searches could easily miss. Directional detectors aim to see a wind pattern from the galaxy. A true smoking gun would not only count events, it would point. Directional detection aims to measure the direction of a recoil track, which could reveal whether events come preferentially from the direction our solar system is moving. Through the Milky Way, backgrounds from radioactivity tend to be directionless in the same way, so a clear directional anisotropy would be incredibly persuasive. The challenge is that recoil tracks are tiny. In dense materials, they can be shorter than a human hair by many orders of magnitude. So directional detectors often use low-pressure gas, where tracks become longer and can be reconstructed. Some designs read out ionization trails with fine resolution, and others use novel approaches to infer direction from asymmetric charge patterns. Even with low event rates, a directional signature could build confidence quickly because it connects the signal to galactic motion rather than local conditions. It is a beautiful concept. If dark matter is a wind, then the best proof is a weather vane. If dark matter annihilates, space telescopes might catch excess gamma rays. Some candidates are their own antiparticles, which means that when two meet, they could annihilate and produce high-energy photons. Gamma rays travel straight and can cross the galaxy, so space telescopes can map them and look for unusual excesses. The most promising regions are places where invisible mass is densest, since annihilation rates rise strongly with density. Dwarf spheroidal galaxies are especially interesting targets because they appear rich in dark matter and have little other gamma-ray activity. Scientists look for a spectrum that matches what annihilation models predict and for signals that appear in multiple dwarfs with consistent properties. The difficulty is that the gamma-ray sky is full of astrophysical sources, including pulsars and supernova remnants, which can masquerade as particle physics. So the analysis becomes a careful competition between hypotheses. Still, the allure remains powerful. It is the idea that the invisible might occasionally erase itself in flashes, and that those flashes could be seen from orbit as a faint telltale glow. The galactic center shows puzzling gamma emission that could have multiple causes. The center of the Milky Way is crowded, energetic, and complicated, which makes it both tempting and treacherous for dark matter searchers. Gamma-ray maps show an excess of emission in the inner region that has fueled years of discussion. One explanation is dark matter annihilation, because the center is expected to be dense in invisible mass. Another explanation is a population of faint astrophysical sources, such as millisecond pulsars, whose combined emission could mimic a smooth glow. There are also diffuse processes involving cosmic rays interacting with gas and radiation fields, which can produce gamma rays with spatial patterns that are hard to model perfectly. Researchers test these ideas by studying the shape of the emission, its spectrum, and how it correlates with known structures in the inner galaxy. The story matters because it demonstrates how high the bar is. A hint is not enough. The sky must be interrogated until ordinary explanations are either confirmed or exhausted. Only then can a particle interpretation stand confidently. Dark matter decay could produce faint X-rays in the cosmos. Some dark matter candidates are not perfectly eternal. They could be so long-lived that most survive for the age of the universe, yet a tiny fraction might decay, releasing a photon with X-ray energy. If that happens, the signal would be subtle, like a barely audible tone spread across the sky. Astronomers would look for a very specific feature, a narrow line at a particular energy, appearing in places where invisible mass is abundant. Galaxy clusters are especially tempting, because they hold enormous amounts of unseen matter in a compact region of sky. The trick is that hot gas also produces X-rays, and its spectrum can be busy. That forces careful comparisons between different targets and different instruments. If a consistent line appeared with the right scaling, it would be astonishing. It would mean the hidden mass is not only pulling on the universe, it is also slowly whispering light into it. A mysterious X-ray line has been argued over for years. A few studies have reported an unexplained X-ray feature that seems to show up in some observations of galaxy clusters and other massive systems. The excitement is easy to understand. A persistent line could be a signature of a decaying dark matter particle with a specific mass. The caution is just as important. X-ray telescopes must be calibrated with extreme care and faint instrumental features can masquerade as real astrophysical lines. Ordinary atomic emission from hot gas can also be misidentified if the modeling is slightly off. That is why the debate has lasted. Different teams, different datasets, and different analysis choices can lead to different conclusions. This is not a story of one dramatic detection. It is a story of scientific tension, where evidence is weighed and reweighed until the simplest mistakes are ruled out. If the line is real, it could open a new window. If it is not, the process still sharpens the entire field. Neutrino telescopes can test dark matter captured inside the Sun. The Sun is not only a light source, it could also be a trap. If dark matter particles occasionally collide with ordinary matter, a small fraction passing through the Sun could lose energy and become gravitationally captured. Over time, those particles would sink toward the center, building a dense reservoir. If they can annihilate with each other, the products would mostly be absorbed by solar material. Neutrinos are the exception, because they can escape from deep inside and reach Earth. That is why detectors buried in ice or water watch for neutrinos coming from the Sun's direction, especially at energies that do not fit standard solar processes. A clear excess would be a dramatic sign, linking a particle interaction to an astrophysical body we know intimately. The beauty of this approach is that the Sun does the concentrating for us. It turns an invisible diffuse halo into a potential point source. If captured particles annihilate, they could create neutrinos that escape. Annihilation inside the Sun would not be a fireworks show you could see. It would be more like a hidden furnace producing messengers that slip through everything. Neutrinos are almost impossible to stop, which makes them both frustrating and valuable. A neutrino telescope looks for the faint flashes created when a neutrino interacts near the detector, producing a charged particle that leaves a track. By reconstructing the track's direction, scientists can ask a simple question. Do more neutrinos seem to come from the Sun than expected? The answer depends on a chain of physics, including how often dark matter scatters in the Sun, how efficiently it accumulates, and what annihilation channels are available. That complexity is a strength, because it provides multiple ways to test models. Even a non-detection is informative. It can rule out interaction strengths that might be hard to probe in underground recoil experiments, making the Sun a complementary laboratory. Colliders try to create dark matter, then infer it from missing momentum. In a particle collider, energy is concentrated into tiny volumes, and new particles can be produced if nature allows it. The challenge is that a dark matter particle would not leave a direct signal in the detector. It would pass through, like a quiet thief. So collider searches look for imbalance. If particles are produced in a collision, their momenta should add up in a way that balances in the plane transverse to the beams. If something invisible carries momentum away, the event looks lopsided. Physicists often search for a visible companion, such as a jet of particles or a high-energy photon, recoiling against the missing momentum. That creates a clean tag that the detectors can register. The difficulty is that standard processes can also produce missing momentum, especially when neutrinos are involved. So the work becomes a careful sorting of possibilities. If a consistent excess emerged in multiple channels, it would be a thrilling hint that dark matter can be made in the laboratory. The Large Hadron Collider has not yet found a clear dark matter signature. So far, the LHC has delivered breathtaking discoveries, yet it has not provided a decisive signal that points straight to the cosmic missing mass. That absence has consequences. It pushes theorists away from the simplest scenarios where dark matter couples strongly enough to be produced often and detected through straightforward missing energy signatures. It also encourages broader searches, including lighter candidates, more elusive interaction types, and models where new particles decay through longer B. chains before producing invisible states. The LHC can still constrain many ideas by setting limits, and those limits guide what underground detectors and space telescopes should prioritize. It is easy to think of non-detection as disappointment, but it is also a form of map-making. Each analysis carves away a region of the unknown. Dark matter may be hiding behind weaker couplings, higher masses, or a more complex dark sector than originally imagined. The LHC is helping narrow the path through that maze. Some theories place dark matter in a whole hidden sector with its own forces. It is possible that dark matter is not a lone particle drifting in silence. It could belong to a richer hidden world, with its own versions of forces and force carriers. In that picture, ordinary matter is not the whole story of particles and interactions. It is only one neighborhood. A hidden sector could allow dark matter to scatter, cool, or form structures in ways that are invisible to our telescopes, except through gravity. Some models even allow a faint connection between sectors, like a narrow doorway that lets a small amount of interaction occur. That doorway might be what experiments are trying to detect. The allure here is depth. If a hidden sector exists, discovering dark matter would not be the end of the mystery. It would be the beginning of a new branch of physics, with its own chemistry of sorts and its own history in the early universe. The cosmos might contain an entire parallel set of ingredients, shaping galaxies while remaining largely unseen. Dark matter might include multiple species, not one simple particle. Nature rarely keeps things simple. Ordinary matter is not one particle. It is a whole family with electrons, quarks, neutrinos, and more. Dark matter could be similar. There might be a dominant component that supplies most of the mass, plus additional species that contribute smaller fractions and leave different signatures. That could help explain why searches have not converged on one clear signal. Different experiments are sensitive to different masses and interaction types, so a multi-component dark sector could be slipping between the cracks. It could also affect cosmic structure. A colder component might build small-scale clumps, while a warmer component smooths certain features. Even within galaxies, multiple species might settle into different distributions if they interact differently. The idea invites a shift in mindset. Instead of asking, "What is the particle?" we might ask, "What is the population?" If dark matter is a mixture, the path to discovery may involve combining several faint hints rather than finding one single smoking gun. It might even form rare-bound states, like dark atoms. If a hidden sector contains more than one particle type, it might allow binding, the way protons and electrons bind into atoms. In a dark sector, particles could carry a hidden charge and feel a hidden electromagnetic-like force. Under the right conditions, they could form bound states, creating something loosely analogous to atoms or molecules, though without emitting ordinary light. This possibility is fascinating because it changes what dark matter could do. Bound states could scatter differently, cool differently, and clump differently from a simple gas of particles. They might also create distinctive signals if there is a tiny mixing between dark photons and ordinary photons, allowing rare conversions or energy injections. Astrophysical observations could then constrain how much cooling or self-interaction is possible, because too much would alter galaxy shapes or cluster behavior. The concept is a reminder that invisibility does not guarantee simplicity. The dark could have structure, and that structure could matter. Dark photons are hypothetical messengers between hidden matter and ordinary electromagnetism. If there is a hidden sector with a force like electromagnetism, it would have its own force carrier, often called a dark photon. On its own, that would remain completely hidden from us. The intrigue comes from the possibility of a small mixing between the dark photon and the ordinary photon. That mixing would be like a faint crosstalk between two radio stations. It could allow tiny interactions between dark matter and charged particles, offering new ways to search. Some laboratory experiments look for missing energy and precise measurements, while others search for subtle signals in electromagnetic cavities, fixed target, setups, or rare decays. In space, dark photon scenarios can be constrained by how they would affect stars, supernova, or the early universe's thermal history. What makes dark photons compelling is their role as a bridge. They offer a physically motivated way for the dark world to remain mostly separate, while still leaving a small, testable thread that could connect it to our instruments. Dark matter's density near Earth is estimated from stellar motions. Astronomers cannot scoop up a sample near Earth, so they use the Milky Way as the measuring device. Stars near the Sun bob up and down through the galactic disk, and they also drift sideways in ways that reflect the local gravitational pull. If there is more mass in the neighborhood, stars are held more tightly, and their motions change in predictable ways. Researchers combine precise positions, distances, and velocities from star surveys. Then they build dynamical models that include the disk, the gas, and an unseen component. The goal is to infer how much invisible mass must be present in our region of the halo. This local density matters because it sets the expected flux through detectors on Earth. It is astonishing that by watching starlight move, we can estimate how much unseen matter is passing through our own corner of the galaxy. Even that local density has uncertainty, which affects detector expectations. Even with excellent star maps, the local estimate comes with wiggle room. The Milky Way is not a perfectly calm system, and our neighborhood contains streams, moving groups, and lingering signatures of past mergers. Small uncertainties in distances or in the mix of stellar populations can shift the inferred gravity, and that shifts the implied invisible density. There is also uncertainty in the shape of the halo and in how the visible disk mass is distributed. These details matter because detection experiments convert density into predicted event rates. A slightly higher density means more chances for a rare collision. A slightly lower density means the same detector could wait longer without seeing anything, even if the particle model is correct. This is why particle searches and galactic astronomy are linked. Better maps of local gravity do not merely refine astrophysics. They directly adjust the expectations for laboratory experiments that are listening for the faintest taps from the dark. The Milky Way's halo may contain streams from ancient mergers. Our galaxy grew by eating smaller systems. When a dwarf galaxy fell in long ago, its stars did not all sink neatly into the disk. Many were stretched into long streams that still orbit in the halo. Those stellar streams are visible signposts of ancient mergers, and they suggest that invisible debris came along for the ride. In many models, the dark component from the accreted dwarf becomes a stream as well, although it is harder to keep narrow because it does not cool or shine. Over time, several such events could leave a layered halo with substructure, rather than a perfectly smooth distribution. This history matters because the halo's present state is not only about what dark matter is. It is also about how the Milky Way assembled. Every merger writes a chapter, and some of those chapters may still be passing through our neighborhood as coherent flows. Those streams could slightly change the speed distribution near Earth. Direct detection depends on relative speed. A detector is more sensitive to particles moving fast enough to deliver detectable energy. If the local halo were perfectly smooth, the speed distribution would follow a simple expectation. If a stream passes nearby, it could add an extra bump, a preferred velocity that changes the predicted recoil spectrum. It could also shift the timing and shape of any annual modulation signal, because a stream has its own direction and speed through the solar neighborhood. The effect might be subtle, yet even subtle changes matter when experiments push into very low event rates. Astronomers look for these possibilities by studying nearby halo stars, since the stars can trace past accretion events that might also have delivered darkened sheen, matter streams. In this way, the Milky Way's archaeological record could influence what a detector should hear. A stream would mean the dark is not only present, it is moving past us with memory of its origin. Dark matter might clump into mini halos that passed through long ago. If structure builds from small to large, then the halo should contain not only smooth background material, but also remnants of the earliest clumps. Some of those clumps could be tiny by cosmic standards, yet still massive enough to have gravitational influence. Over billions of years, many would be shredded by tides and encounters. Others might survive as compact mini halos that roam the larger halo like invisible islands. If one passed through the solar neighborhood, it could briefly raise the local density. That would change detection rates for a time, like drifting through a fog bank. The passage could also leave gravitational signatures in fragile systems, depending on the clump's mass and trajectory. This idea is exciting because it makes the dark matter environment dynamic. The search is not only for what dark matter is, it is also for how it is arranged in space and whether our region is typical or temporarily unusual. Some clumps could survive without stars, becoming truly invisible subhalos. Many subhalos may never have formed stars at all. A small halo can struggle to hold gas, especially once the universe becomes filled with energetic radiation that heats and strips material. Without gas, no new stars form. Without stars, the halo is dark in every normal wavelength. Yet its gravity remains. It can still perturb orbits, bend light, and influence nearby structures. This possibility is a cornerstone prediction of several dark matter models, and it offers a rare chance to test them using gravity alone. Astronomers search for invisible subhalos by watching for oddities in stellar streams, and by examining lensing systems where light behaves as if small clumps are present. The idea is almost eerie. The Milky Way could be filled with countless companions that are real, massive, and entirely unseen except through their pull. If we confirm them, it would be a direct glimpse of dark matter structure on small scales. Lensing of quasars can reveal these subhalos through flux anomalies. Quasars are distant, brilliant beacons powered by supermassive black holes. When a galaxy lies in front of a quasar, gravity can split the quasar into multiple images. In a smooth lens, the brightness ratios of those images should follow predictable patterns. Sometimes they do not. One image is too bright or another is oddly dim compared with the smooth expectation. These mismatches are called flux anomalies. A leading explanation is that small clumps of mass in the lensing galaxy, including dark subhalos, are perturbing the light paths. This method is powerful because it can detect substructure even when the clumps contain no stars. It uses a quasar as a backlight and gravity as the sculptor. Care is needed, since stars in the lensing galaxy can also cause microlensing that affects brightness. Still, when the evidence lines up across wavelengths and models, flux anomalies become a clever way to count invisible lumps in distant halos. The smallest dark matter structures depend on the particle's early behavior. The universe's tiniest building blocks are not set by telescopes alone. They are set by microphysics. If dark matter had significant thermal motion early on, it would stream out of small density peaks and erase them. If it behaved like a field with wave properties on astrophysical scales, it could suppress very small clumps in a different way. If it interacted with itself, it could alter how concentrated small halos become. Each candidate leaves a different cutoff scale for the smallest structures that can form. That cutoff is like a fingerprint. Astronomers infer it by studying the abundance of small galaxies, the fine structure of lensing, and the behavior of intergalactic gas that traces small scale. Clustering. This is thrilling because it turns the cosmos into a particle detector. You might never catch a particle in the lab, yet you could still deduce its early behavior from the presence or absence of tiny gravitational structures across the universe. The first halos may have been tiny, then merged into larger ones. Cosmic structure formation is often described as hierarchical. Small gravitational wells form first, then they collide and merge, building larger halos over time. In that story, early halos were the seeds from which galaxies would later grow. Many of those first halos may never have made many stars, yet they still mattered. They were the scaffolding that gathered gas and set the stage for later star formation in deeper wells. As time passed, mergers built the halos of modern galaxies, including the Milky Way. This means our galaxy's halo is a layered object. It carries the history of countless mergers, accretions, and tidal disruptions. Some debris becomes smooth background. Some remains as coherent substructure. The process is not only about adding mass. It is about mixing, stirring, and reshaping what is already there. When we model today's halo, we are reading the end state of a long chain of cosmic assembly. This merging history is written into the distribution of galaxies today. Look at a deep map of the universe, and you see clustering at many scales. Groups sit inside filaments. Filaments connect to clusters. Voids separate the busiest regions. That pattern is not accidental. It is the outcome of billions of years of merging and growth. When halos merge, they do not only combine mass, they also bring in galaxies, gas, and orbital energy, which shapes future evolution. The statistics of galaxy clustering, including how likely a galaxy is to have neighbors at a given distance, encode that growth history. So do the masses of clusters and the abundance of massive halos at different cosmic times. By comparing observations to simulations, astronomers can test whether the merging story is consistent with different dark matter models. A model that changes small-scale structure will change the merger tree, and that will change the galaxy distribution we see. In this sense, every galaxy survey is also a fossil record of dark matter assembly, written across the sky in positions and patterns. Dark matter helped reionization by gathering gas where the first stars ignited. Long before galaxies looked like the ones we know, the universe went through a makeover. Neutral hydrogen filled space, and it absorbed energetic light easily. Then the first star-forming pockets began to switch on, and their ultraviolet radiation started stripping electrons from that hydrogen again. That era is called reionization, and it is one of the great turning points in cosmic history. The key is that the earliest stars needed places where gas could collect fast enough to collapse. Invisible halos provided those first gathering basins, pulling in hydrogen and helping it reach the densities where cooling and collapse could begin. Once the first generations of stars formed, their light-carved growing bubbles of ionized gas into the surrounding darkness. Those bubbles expanded, merged, and gradually transformed the universe into something transparent and bright. Reionization is a story about light, yet its opening chapters were written by gravity you could not see. It influences when the first galaxies formed and how fast they grew. In the early universe, timing is everything. A small change in how quickly matter gathers can determine whether the first galaxies appear early or arrive late and sparse. Invisible mass affects this timing by setting how quickly gravitational wells deepen and by shaping how often young halos merge into bigger ones. Faster early growth means earlier gas inflow, earlier star formation, and a quicker buildup of the first luminous islands. Slower growth means fewer early wells and more difficulty assembling the first galaxies before the universe ages. This is why astronomers care about the faintest galaxies at extreme distances. They are not only pretty, they are clocks. Their existence and abundance hint at how efficiently structure formed when the universe was young. When models change the small-scale behavior of the invisible component, the predicted timeline shifts. The first galaxies become a direct test of what the unseen mass was doing while everything else was still taking shape. Early galaxy counts from powerful telescopes test dark matter models. Counting galaxies might sound simple, yet at the edge of the observable universe, it becomes a sharp test of fundamental physics. The most distant galaxies are faint and small, and their light has been stretched by cosmic expansion into infrared wavelengths. Modern observatories can now detect many of these early systems and build a census across different brightness levels. That census carries a message. If early structure formed efficiently, there should be more small galaxies, more early star formation, and a steeper rise in counts at the faint end. If small-scale structure was suppressed, the universe should look emptier at the same epoch. Astronomers also compare how clustered these early galaxies appear, since clustering reveals how massive their host halos must be. The beauty is that a simple inventory becomes a discriminator among ideas. The early universe cannot be bribed. It either contains the predicted number of galaxies, or it does not. The Lyman alpha forest records small-scale structure in intergalactic gas. Between galaxies, space is not empty. It is threaded with thin clouds of hydrogen that absorb light at specific wavelengths. When we look at a distant quasar, that quasar's light passes through many such clouds on its way to us. Each cloud removes a tiny slice of the spectrum, producing a long comb of absorption lines known as the Lyman alpha forest. The spacing and strength of those lines depend on how matter is distributed on relatively small scales. If small-scale structure is rich, the forest is busy and varied. If small-scale structure is smoothed, the forest becomes more uniform. This makes the Lyman alpha forest a sensitive probe of how the invisible component behaved early on, especially for models that change the abundance of small clumps. It is astonishing that a quasar spectrum, a simple line plot of brightness versus wavelength, can carry information about unseen structure spread across billions of light years. Gravitational lensing time delays can weigh galaxy halos with precision. When a distant quasar is lensed into multiple images, those images are not perfectly synchronized. Light travels along different paths through warped space, and those paths have different lengths and different gravitational time delays. If the quasar flickers, the flicker appears in each image at a slightly different time. By measuring those delays, astronomers can constrain the lens's mass distribution with impressive precision, because the delays depend on how deep the gravitational potential is along each path. This method is especially powerful because it can probe the inner structure of a galaxy halo where ordinary matter and invisible matter both contribute. It also provides cross-checks on other lensing measurements, since geometry, brightness, and timing must all agree. The work is demanding. It requires long monitoring campaigns and careful modeling of the lens environment. Yet the reward is elegant. Time itself becomes a measuring tape for invisible mass. Cluster lensing maps show peaks of mass that do not match light. In massive clusters, lensing can produce a detailed mass map that is almost like topography. Using the distortions of many background galaxies, astronomers reconstruct where the gravitational peaks must be. Then they compare that map to what shines, including galaxies and hot gas. The comparison can be startling. Some regions with strong lensing signal do not correspond to obvious concentrations of luminous matter, while bright regions can sit off to the side of the CAR. Deepest mass wells. This matters because lensing is sensitive to total gravity, not to temperature, chemistry, or brightness. It therefore acts as an independent judge of where the weight is. These mass maps also reveal the cluster's internal substructure, including smaller mass concentrations that may be in falling groups. Each peak is a clue to assembly history, and each mismatch between mass and light is a reminder that the universe's main ingredient is not the one that glows. The bullet cluster remains a famous case where mass and gas separate. This system became iconic because it turned a complex argument into a clear demonstration that many different observers could analyze. It combined deep imaging, X-ray measurements, and gravitational lensing into one story that could be checked from multiple angles. Researchers used background galaxy distortions to reconstruct where the gravitational mass concentrates, and they compared that to where the normal matter dominates. The result was persuasive enough that it entered textbooks and public science talks, not as a final proof, but as a vivid benchmark. It also shaped how people evaluated alternative explanations. Any theory that tries to remove the need for unseen mass must still reproduce what lensing sees in this and similar systems. Over time, the bullet cluster has served as a calibration point for analysis methods, a target for repeated observations, and a reference for new simulations of cluster mergers. Its lasting power comes from how many lines of evidence converge in one place. Similar merging clusters provide more tests of collisionless behavior. One dramatic example can be memorable, yet science becomes stronger when it turns one story into a population study. Astronomers now search for other merging clusters with different collision speeds, viewing angles, and mass ratios. Each geometry changes what should be observed, and that helps separate robust effects from chance alignments. In some systems, the merger is nearly in the plane of the sky, which makes lensing maps easier to interpret. In others, the collision has a strong line of sight component, which challenges reconstruction methods and forces new modeling approaches. By comparing many mergers, researchers can ask whether the invisible component behaves as largely collisionless across a range of conditions, or whether subtle deviations appear. They also examine whether the inferred mass distribution shows consistent shapes and concentrations that match expectations from simulations. This shift from a single showcase to a catalogue of tests is crucial. It turns a compelling case into a disciplined pattern, and patterns are what physical laws tend to leave behind. If dark matter self-interacts, cluster collisions can limit that strength. If invisible particles scatter off each other, even slightly, then a cluster merger becomes a high-speed laboratory. During a collision, self-interaction could create a drag effect, redistribute mass, or reduce the central density in ways that lensing could detect. Researchers translate the absence of strong drag signatures into limits on how frequently such scattering could occur. These limits are valuable because they probe interaction strengths that are difficult to test in underground experiments, especially if the particles interact mainly with themselves rather than with ordinary atoms. The analysis is subtle. It must account for projection, substructure, and the complexity of real mergers. Yet the basic idea is powerful. Clusters are enormous, their relative speeds are extreme, and their dark matter content is large, so even rare self-interactions could accumulate into visible consequences. By not seeing certain types of redistribution, we learn what dark matter cannot be, and that narrows the search for what it is. Some models predict dark matter would leave offsets or tails during mergers. In models with self-interaction, the invisible component can behave less like a perfectly ballistic swarm and more like a medium that can develop wakes. During a merger, scattering could create a trailing tail of mass, or shift the peak slightly behind the most collisionless traces. Other models predict more complex features, such as a broadened mass distribution or asymmetric extensions that persist after the main impact. Observers look for these signatures by comparing precise lensing maps to the locations of galaxies, gas, and inferred dynamical centers. The challenge is that real clusters are messy. and projection effects can create apparent offsets even without new physics. That is why researchers combine simulations with targeted observations, asking what features should be long-lived, what should be rare, and what should scale with collision beta. Speed. The exciting part is that this is not a vague hunt. The models make shapes. The sky either contains those shapes or it refuses to. Modified gravity ideas try to avoid dark matter, yet clusters still challenge them. Some scientists have asked a bold question. What if the laws of gravity change on very large scales, so the missing mass is an illusion? These modified gravity ideas can be tuned to reproduce certain galaxy rotation patterns without adding unseen matter. The trouble arrives when you zoom out to galaxy clusters. Clusters contain galaxies, hot X-ray gas, and lensing signals that together point to a large gravitational budget. In many cases, the amount and placement of gravity inferred from lensing does not line up with where the ordinary matter sits. That mismatch is difficult to fix with a simple change in gravity alone, because lensing cares about the total curvature of space. Clusters therefore act like stress tests. They are messy, massive, and unforgiving. Even if modified gravity captures part of the story, clusters often seem to demand an extra component that behaves like real, unseen mass. Any alternative must explain the cosmic microwave background peaks convincingly. The cosmic microwave background is not just a glow. It is a pattern of peaks and troughs in temperature variations that acts like a fingerprint of the early universe. Those peaks reflect sound waves in the primordial plasma, with gravity pulling inward while pressure pushes outward. The precise heights and positions of the peaks reveal how much normal matter existed, how much radiation mattered, and how much extra gravitational pull was present without coupling to light. Any alternative to dark matter must reproduce this entire pattern, not merely one feature. That is a hard demand, because the microwave background is measured with extraordinary precision, and many different pieces of physics must fit together at once. If you change gravity, you must still match how structures began to grow, how light propagated, and how the universe's contents shaped those early Tetham oscillations. The microwave peaks are like a locked safe. Any theory that claims the prize must know the combination. Dark matter is not the same as dark energy, despite the names. The names sound similar, and that confusion is common, but they describe very different cosmic roles. Dark matter behaves like additional mass. It gathers, it clumps, and it strengthens gravity in the places where structure forms. Dark energy behaves more like a property of space that drives the universe's expansion to speed up over time. One of them helps build cosmic structure. The other pulls space apart on the largest scales. They also show up in different kinds of evidence. Dark matter is inferred from motions, lensing, and the way structures grow. Dark energy is inferred from the expansion history, including how distant supernova and large-scale patterns change with time. Keeping them distinct is important, because solving one mystery does not automatically solve the other. It is possible that dark matter is a new particle, while dark energy is vacuum energy, or something even stranger. Two shadows, two different sources. Dark energy drives cosmic expansion, while dark matter clumps and pulls inward. Think of the universe as a vast stage where two opposite tendencies play out. One tendency gathers matter into galaxies, clusters, and filaments. The other tendency stretches the stage itself, increasing the distances between faraway regions. Dark matter belongs to the gathering side. It is the inward pull that helps structure grow from small beginnings. Dark energy belongs to the stretching side. It becomes more important as the universe expands and matter thins out, and it changes the long-term fate of cosmic growth. This tug-of-war leaves observable traces. If the expansion accelerates too strongly, it can slow the rate at which new structures form, because matter has a harder time collapsing against the growing separation of space. That means measurements of structure growth over cosmic time help constrain both components together. It is a beautiful interplay. One ingredient builds the cosmic cities. The other shapes the cosmic highways between them. Future surveys will map billions of galaxies to refine dark matter's fingerprint. The next era of cosmology is a census on an almost unimaginable scale. By mapping enormous numbers of galaxies, surveys can measure how clustering changes with distance and direction, which reveals how matter is distributed and how it evolved. The key is statistics. Subtle effects become clear when you have huge samples, and dark matter leaves subtle effects everywhere. It influences how galaxies group into clusters, how voids expand, and how lensing distortions accumulate across the sky. With enough galaxies, researchers can compare observations to simulations with much tighter error bars, testing whether small-scale predictions hold and whether the D invisible component behaves as expected. These surveys also help disentangle biases, because galaxies are imperfect tracers of total mass. You need many types across many environments. The result is that dark matter becomes less of a single mystery clue and more of a detailed pattern, like a fingerprint with ridges you can trace. More data does not just add confidence, it adds texture. The Rubin Observatory will track sky changes that aid lensing and structure studies. Rubin will not only take deep images, it will take them repeatedly, building a time-lapse of the sky. That matters for dark matter, because repeated imaging improves shape measurements for weak lensing, and it also reveals transient events that can be used in precision studies. With many visits, astronomers can average down atmospheric effects and improve calibration, which is crucial when you are searching for tiny distortions in D. Galaxy shapes. Rubin will also discover large numbers of supernova and other variable sources, which can help map cosmic expansion and provide cross-checks on structure. Growth. Another powerful contribution is the discovery of faint satellite galaxies and stellar streams in the Milky Way, which sharpen small-scale tests of halo structure. Rubin's strength is breadth and consistency. It will watch large regions of sky with a stable system, turning the night into a long, coherent dataset rather than a patchwork. For dark matter, that kind of uniformity is precious. The Euclid mission will map large-scale geometry and dark matter with lensing. Euclid is designed to do something that ground-based telescopes struggle with. It will measure galaxy shapes from space with extremely stable imaging, which is ideal for weak lensing. It will also gather information about galaxy distances through its surveys, which lets researchers build a three-dimensional picture of how structure distributed across cosmic time. With those two ingredients, Euclid can trace how the invisible mass web grew as the universe expanded. That growth rate is sensitive to the amount and behavior of dark matter, and it also interacts with the influence of dark energy. Euclid's large area coverage is a major advantage, because lensing signals are statistical and require huge numbers of background galaxies. By combining shape measurements with distance information, Euclid can separate what is nearby from what is far, revealing how the gravitational landscape changes with redshift. In a sense, Euclid aims to turn lensing into cartography, not a picture of light, but a map of weight. The square kilometer array will trace hydrogen patterns that follow dark matter wells. Hydrogen is the most abundant element, and it carries a special beacon. Neutral hydrogen emits radio waves at a wavelength of 21 centimeters, which can be used to map vast regions of the universe. The square kilometer array will use this signal to trace large-scale structure in a way that complements optical galaxy surveys. Hydrogen tends to collect in gravitational wells, so its distribution follows the underlying matter field, including the invisible component that provides data to know most of the gravity. By mapping hydrogen over enormous volumes, SCAR can measure patterns such as Barrean acoustic oscillations and the overall clustering of matter. It can also probe cosmic epochs that are difficult to reach with optical observations, offering a different window on when and how structure formed. This is exciting because it changes the tracing method. Instead of counting galaxies one by one, you can map the medium between them. Hydrogen becomes a cosmic fog that outlines the shape of gravity itself, and gravity is where dark matter lives. If we identify the particle, we will rewrite the inventory of the universe. Right now, the cosmic budget is partly a list of known things and partly a confession of ignorance. We can estimate how much ordinary matter exists. We can infer how much dark matter must exist. Yet the nature of that dominant mass remains unknown. Identifying the particle would convert a major category from placeholder to substance. It would tell us what the universe is actually made of, not just how it behaves. It would also reshape physics. A confirmed particle would need a production mechanism in the early universe, a stability explanation, and a place in a broader theory. It might reveal hidden symmetries or new forces, or it might require a revision of how we think about matter beyond the standard model. The consequences would reach outward too. Galaxy formation models would gain a real microphysical foundation. The word dark would lose its vagueness. It would become a name, with properties you can write on a chalkboard and test in a lab. Solving dark matter could reveal a hidden world of physics beyond the standard model. The standard model is one of the most successful scientific frameworks ever built, yet it does not contain a good dark matter candidate that fits the cosmic's evidence. That gap is not a small omission. It suggests that there is more to reality than our current particle roster. Solving dark matter could therefore open a doorway into a wider theory, one that explains not only the missing mass but also why the known particles have the ID, properties they do. The discovery could point to new symmetries, new fields, or new kinds of interactions that were previously invisible to our instruments. It could also change how we interpret astrophysical phenomena, because a richer dark sector might have its own subtle behaviors that shape galaxies in ways we have not yet recognized. The best part is that the clues come from everywhere, from underground detectors to quasar lensing to the microwave sky. When one solution ties those threads together, it will not feel like adding a patch. It will feel like revealing a deeper layer of nature. As we come to the end of our journey, take a moment to notice how vast it all has been. We began with galaxies spinning too fast to hold themselves together, and followed that mystery outward into clusters, filaments, and the great web that stretches across the observable universe. We drifted through ideas born almost a century ago, through careful measurements of stars and light, and into modern experiments buried deep beneath the Earth. Again and again, the same story appeared. Something unseen is shaping everything we observe, guiding the growth of galaxies, bending light, and leaving subtle fingerprints across space and time. Dark matter is not a single image you can hold in your mind. It is a presence, a background weight, a quiet architecture that gives the cosmos its form. From the smallest dwarf galaxies to the largest clusters, from the first stars to the future surveys still being built, its influence connects every scale into one unfolding pattern. It reminds us that the universe is deeper than it looks, and that much of reality reveals itself only through patience and careful listening. Now, there is nothing left to solve. No need to remember details or names. Let the ideas soften and blur, like distant lights seen through a window at night. Feel the steady rhythm of your breathing, and allow the sense of wonder to settle into calm. The universe will keep turning, galaxies will keep drifting, and the answers will wait. If you enjoyed this journey, you might like to explore another before sleep fully arrives. A new video is waiting on the screen, should you wish to continue. And if you feel like it, liking or subscribing helps others find their way here as well. For now, let the darkness feel spacious rather than empty, and let your thoughts slow with the turning of the stars. Sleep well, and good night.